All right. So this is week of April 8th, right? And we are testing this week. So April 8th through the 12th, these dates are not correct. So let me cross these off. So this is 8th through the 12th. I'll be back on the Monday the 15th. Okay. So we're going to look at some of the definitions for thermal energy. All right, so let's take a look at the first one, kinetic theory of matter. All matter is made up of small particles and constant random motion. So if you take a look at my PhET sample here, this is a container that has temperature scale on it, so Kelvin, Celsius. So this is minus 127 degrees Celsius. So water in its solid form. Now notice they are still vibrating, right? And they are vibrating because they have energy, kinetic energy, energy of motion. Now, as we move to liquid water, you'll notice the temperature changed. Here we have it now at 13 degrees Celsius, so it's not 0 degrees Celsius is where it becomes solid. We had it lower than that, but you notice that there's much more activity. So the kinetic theory of um, molecules or particles says that all objects vibrate, whether they're vibrating in place, but the kinetic theory that goes along with this means there is more motion in the liquid and gas phases than there is in the solid phase. So here we have less activity, right? So if we heat this up to melt it, right? So we're going to get it to 0 degrees Celsius. And now we have a liquid form at 3 degrees. You'll notice that adding heat to it has made it solid go to a liquid. More movement. Let's boil it. Go to the boiling point, 100 degrees Celsius. And you notice that we're getting more and more kinetic energy. We're adding heat to it, right? 65, 100 degrees Celsius is the boiling point. And notice that we're losing, so molecules, particles are moving around more, and they're leaving the confined space that they were in, right? And now this is the most energy here. Okay, if we cool it down, we can lower the amount of kinetic energy. Remember, kinetic energy is motion. So 0 degrees, minus 45, bring it into, and then if we were to get it to minus 273 degrees, or that is zero, absolute zero, there is no movement. We still have some movement there. Pretty hard to get it down to minus 273 degrees in real life. Okay, so let's take a look at what we just had there. All matter is made of small particles, constant random motion. And then thermal energy equals the kinetic energy with which the vibrations of the particles. Thermal energy, we can measure the thermal energy by looking at the total energy in the system. Now, temperature, on the other hand, measures the average kinetic energy of a particle. It does not depend on size. So average, we put a thermometer in something and we can measure the particles that are around the thermometer. We're not measuring the energy, we're measuring the average kinetic energy of some individual particles next by, where kinetic energy is the total, or the thermal energy is the total number of particles that are vibrating. So we're looking at the total particles. Here we're just averaging out what individual particles are saying. They're all about this. Okay, so let's take a look at this next one, where we're looking at heat is equal to thermal energy that flows from warmer places to cooler places. So I have this, okay, lab here to kind of show you. Okay, we're going to use conduction, so we're going to actually touch some things, right? Normally, even in your room, heat travels from warm things to cold things, and then tries to get at equilibrium where everything has the same temperature. So we're going to touch these two things, and here you can see the red is highly energetic, lots of kinetic energy, should represent a warmer state than the blue, which shows us a cooler state. So, and if we look at the graph here, so the blue is at 0 degrees and the red is at 100 degrees. So when we touch these, you'll notice that the temperature, okay, is going to move from the red, goes from the warm to the cold, or less energy. And notice that we have two, the large pieces, or the same size pieces of material, and we get an average, we're going to get an equilibrium of 50 degrees, right? So 100 degrees plus 0 degrees equals 50 degrees. So how I do that, I add those up. 100 plus 0 is 100, and divide by 2, and that'll give me 50. So again, if I do this, let me reset this. Turn this off here a second, reset this. All right, and I get a smaller piece, or a larger piece. So if I have, let me see if I get this right. So if I have more, a little larger cooler piece, and a smaller warmer piece, put those together, you would expect that their equilibrium would be different, and you would be right. So remember, the warmer goes to the colder. It looks like we're going to end up at 40. So we have 100 degrees and 0 degrees, but the material we don't have near as much. We get 40. So if I think about another question that I could ask here, if I have something that same quantities of material, so this, let's say they're both the same. One was 60 degrees, another was 20 degrees, right? And these blocks are the same size. Let's say they're the same size. Just one is 60 degrees, this one is 20 degrees. I would add those two together, get 80 degrees, and divide that by 2. Sorry about that. Divide that by 2. I get 40 degrees. Right? So again, the main idea here, warm goes to cooler, and they have an equilibrium where they become the same uh, temperature and the same types. The kinetic energy is similar. So you can see that they're all moving at the same rate at this point. Okay. Okay, so we've talked about kinetic theory of matter. All matter is made of small particles in constant random motion. Thermal energy is kinetic energy that comes from the vibration of particles. Temperature is the measurement of those particles, the individual particles, but we'll find an average. And where thermal energy is adding up the total, and heat is the thermal energy that flows from warm places to cooler places. Right, and when we're using our temperature scale, we're going to use uh, Kelvin and Celsius. Celsius most commonly used in science, official SI unit for temperature, and Fahrenheit is not part of the SI system, but we're very familiar with that. So 98.6 is our temperature of our normal body temperature, and we use that all the time. 37 degrees Celsius. Okay, so if we look at these scales here, so here is the scales. You might want to remember these or write these down in your notes. Boiling water, 212 degrees. Water freezes at 32. Absolute zero, where there's um, all vibration stops. So that's a new thing for us to talk about. Vibration of the kinetic energy, there's no thermal energy in it at all, minus 460 degrees. Now, Celsius, the science unit, seems to be much easier to handle when we're doing calculations. 100 degrees is Celsius, 0 degrees for freezing of water, 100 degrees is the same thing as boiling, and minus 273 degrees is your absolute zero. And then Kelvin, we start at 0, that's the absolute zero, and then we add 273 degrees to get it to the 0 degrees Celsius, that's where it freezes, and 373 degrees for water boiling. So the reason that we have these different scales, we started out with, in the beginning of, we had like 23 different scales of thermometers, and these were individually made by um, handy people with glass, and uh, um, and they were the most popular one was the Fahrenheit. Now he chose the 312 degrees and 212 as his numbers, and became very fixed in the United States because we bought lots of those, and he was probably one of the more accurate and probably the maybe the best price point. I'm not sure in that particular case. So we talked about um, energy equilibrium. Two adjacent systems reach the same temperature. Heat flows from the body from greatest thermal energy, the hottest temperature, to the coldest temperature, right? And again, like I was trying to say, if you can have 100 plus 0, right? So this is 100 divided by 2, which gives us the 50. But we could also have something like where we're having the same size or same quantity or same volume of a liquid that's got 80 degrees and um, 30 degrees. So the warm, and then we'll get to equilibrium. We add those two together, we get 110 degrees. Divide that by 2 because of the same size volumes. We get an average temperature of 55 degrees. Right? So that's what we've been talking about so far. Okay, so let's take a look at phase changes for a minute. Now, a phase change is a transformation of matter that from liquid to solid to gas. So a phase change, or another way of calling this, is a change of state, right? Change of state. And a change of state is the three states of matter, all right, that we're going to use. Change of state. Remember, a state is its appearance. So solid, liquid, and gas, right? Okay, so at a phase change, change from solid to liquid gas, the things that you have to remember, temperature of the object stays the same during that change of state. The thermal energy breaks bond between particles, increasing their range of motion instead of increasing their vibration. So we can increase their vibration by adding more heat, but then we get to a point where we're going to break the bonds to change the state from solid to a liquid or a liquid to gas. And it increases their range of motion, but doesn't increase their vibrations. Fixed amount of thermal energy for the phase change to happen different for different substances. Okay, so water, basically what they're saying is water boils at 100 degrees Celsius, but other things will boil or turn to liquid at different temperatures, which makes sense. You know, metals, it takes hundreds of degrees to get them to melt and become a liquid, and then to become a gas. And then there are some things like the oxygen around us is already boiled. It's already a gas. Takes it has a lot. Doesn't take much to get it um, to boil. It doesn't take much energy. Takes a lot of extraction of energy to get it to be a liquid or a solid. So let's take a look at the phase change diagram here. Right. So a phase change diagram. Let me see if I can make this any bigger here. Okay. So here is increasing temperature from 0 to 200 degrees Celsius. And this is increasing energy. So we're adding energy. So when we start at ice water in its solid form, this could be anything as far as any solids, but we're going to use water because water has a range that's within our manipulation. We can freeze things and boil things. All right, so at below 0 to about 0 degrees, it's all solid. At this point, and we're adding increasing energy here. At this point, we are starting to melt that solid. So it's partially solid, partially liquid. Okay, so that's called our melting. And notice that happens at 0 degrees, right? And then when we get through that point, we have we've completely melted everything. So here it's B, we have both solid and liquid. We're overcoming the bonds between them. Okay, so that's why at 0 degrees, we're not increasing the vibration here. We're increasing, we're breaking the bonds between the molecules, the intermolecular bonds, right? We're breaking those bonds. And that's why you'll notice this flat part here basically says the temperature is 0 until it becomes all liquid. When it becomes all liquid, that temperature will rise, putting more energy into the liquid, much more energetic, until we get to 100 degrees Celsius, where we are making it, we're vaporizing it. So it's a combination, it's partly liquid, partly vapor, and we're vaporizing it. And it's flat spot again, because now we're breaking the molecules apart even further. Those bonds we're breaking, and until we get to a point where it's all gas, and then we can make it hotter even still. The gas will get above its boiling point, and as long as we continue to heat the gas. So you also notice that if we come back down, so decreasing the energy, we'll start to, at 100 degrees, we'll start to condense it. So it'll be partly liquid, partly gas. So it's the same temperature. Vaporization and condensation just means that we're reducing the temperature. Here we're vaporization, we're increasing the temperature. Then we get to a liquid state, start to reduce the amount of energy here, and now removing energy, we start to see liquid and solids start to make until the